Hi, in this module I will discuss axial loadings and thermal stresses. Consider this bar. This bar is subjected to axial loads P, that is loads acting along the longitudinal axis of this bar. This load P is tensile load. The bar may also be subjected to compressive axial load like this. This load is compressive axial load. Now we want to find the stresses induced in this bar due to the application of axial load P. To find the stresses, make an imaginary cut in this bar. The imaginary cut is shown by the red line that divides the bar into two parts A and B. Consider part A. Since the entire bar is in equilibrium, therefore part A must also be in equilibrium. To keep the part A in equilibrium, an internal force must be acting on this cross section. The distribution of the internal force will be uniform across the cross section because the load P is passing through the center of cross section. Therefore, the stress on the cross section will be uniformly distributed and it can be given as P by area. Assuming the material to be linearly elastic and isotropic, we can use Hooke's law to find the strain. Epsilon xx is equal to 1 upon E sigma xx minus mu sigma yy plus sigma zz. In this case, there is no stress in the y direction and there is no stress in the z direction because we have only one load which is acting along the x direction. Therefore, we get epsilon xx as sigma xx by E. Now, this strain along the x direction can be written as del u by del x. That is, if we choose a differential element of length dx at any distance x, then the original length of differential element is dx, and after the application of load P, the length of this differential element AB, that is this length, changes by an amount du. So, to write the total change in the length of this entire bar, we can integrate du over the entire bar. So, we get du is equal to sigma xx by E into dx. To get the total elongation of this bar, that is total change in length, we need to integrate du from 0 to L. Therefore, we get total elongation in bar as 0 to L integration of sigma xx by E into dx. Now, using this formula, we can calculate the total elongation of bar subjected to axial loading in many cases. For example, consider case 1 in which a bar of uniform area and constant E. The area is uniform. It means that area A is constant with respect to length. It is not changing over the length of the bar. We have already found that the elongation under axial loading is given by integration 0 to L sigma xx by E into dx. Now, the stress on any cross section sigma xx can be written as P by A. Putting this value here, we directly get sigma xx as P by E A into dx. Now, for this case, since area A is not varying with x and E is also constant, we can take E and A as constant. Therefore, we get dl is equal to P is already a constant. We get this as equal to P by EA integration dx 0 to L. Therefore, we get P by EA into L. So, elongation of a bar of constant area and constant E due to axial load P is given by PL by EA. Consider case 2, in which we have a tapered circular cross-section bar and constant E. This bar is tapered, that is, its diameter is changing from D1 to D2 over the length L. This bar is subjected to axial load P. Now, due to axial load P, if we want to calculate the stresses at any distance x on this cross section, then stress on this cross section sigma xx can be written as the internal force on this cross section, which will be equal to P divided by the area of this cross section. Let this area be the area at any location x. So we can get the elongation as 0 to L sigma xx by E into dx. Now putting this sigma xx in this equation, we can write P by E ax into dx. But since this area is varying with distance x, so we have to express area in terms of x to integrate this equation. Now if we draw this tapered bar, the diameter at x is equal to 0 is d1 and x is equal to L is d2. Let the diameter at any location x be dx. Assuming the variation of diameter to be linear over the length L, we can write that in length L, the change of diameter is d2 minus d1. Therefore, change in diameter per unit length is given by change in diameter per unit length is equal to d2 minus d1 by L. Therefore, change in diameter over length x will be d2 minus d1 by L into x. Now if we see this bar, the initial diameter is d1, here it is d2, and at any distance x, diameter is dx. So we can write this diameter dx as initial diameter d1 plus change in diameter over distance x. The change in diameter over distance x is this. So we can directly write d2 minus d1 by L into x. Therefore, we get area AX of this cross section, that is cross section at any distance x, as equal to pi by 4 dx square, which will be equal to pi by 4 d1 plus d2 minus d1 by L into x whole square. So we have found the area at any distance x. Now putting this area in the equation of elongation del L, that is this equation del L is equal to integration 0 to L P by E ax into dx. We put area ax here, then we integrate to find dl. We get dl is equal to 0 to L P by E into area, which will be pi by 4 d1 plus d2 minus d1 by L into x whole square into dx. Now integrating this, assuming that E is constant as it is given, P is a constant value, therefore we can take them out. We get 4 P by E into pi as common, and the rest is 0 to L dx upon d1 plus d2 minus d1 by L into x whole square. Integrating this, we will get the elongation of tapered circular bar as 4p L divided by pi E d1 into d2. So this is the formula for calculating the elongation in a tapered circular bar of constant E. Now case 3, in which we have a rectangular tapered bar but of constant width B and constant E. So in this case the width B is constant. This is also with B, this is also with B, and this is also with B. But its thickness is changing. Here the thickness is T1 and here the thickness is T2. At any distance x, let the thickness be Tx and let the total length of the bar be L. It is subjected to axial load P. So we want to find the elongation. The formula for elongation under axial load is 0 to L sigma xx by E into dx. Now the stress on any cross section at distance x, that is stress on this cross section, is given by sigma xx is equal to load, which will be P, divided by area of this cross section, that is area at any location x. Now the area of this cross section AX will be equal to width, that is area of this cross section. If we join this, we can find the area of this cross section, this shaded cross section, as width V into thickness T. So thickness at any location x is Tx. The thickness of this is Tx. So again we have to express Tx in terms of x to integrate this equation. Therefore we here write 0 to L P by E B Tx into dx, because sigma xx is P by Ax and Ax can be written as B into Tx. Now if we consider the thickness, this is thickness T1, this is T2, and at any location x this thickness is Tx. Considering the variation of thickness as linear, we can write thickness Tx as initial thickness T1. The change of thickness over length L is T1 minus T2 by L. Therefore, change in thickness over distance x will be T1 minus T2 by L into x. The initial thickness is T1. Change over the length x is this. So the thickness at any location x, that is this thickness, will be T1 minus this. Putting it in the formula of elongation, we get 0 to L P dx by E B into Tx. Tx is T1 minus bracket T1 minus T2 by L into x. Now since E is constant, with V is also constant and P is a constant value, therefore taking them out we can get elongation as 0 to L P by E B integration dx T1 minus T2 by L into x. Integrating this, we will get elongation del L as P L by E B into thickness T1 minus T2 into ln T1 by T2. Remember that thickness T1 is the greater thickness and T2 is the smaller thickness. Now, elongation in cylindrical bar due to self weight. Consider this cylindrical bar which is hanged from the ceiling. This is ceiling and a cylindrical bar is hanged from the ceiling. The length of this cylindrical bar is L. Now the formula for elongation is given by 0 to L sigma xx by E into dx. The weight of this bar will be acting like this, which is an axial load on this bar. Due to this axial load W, which is the weight, this bar will elongate by some del L. To find the elongation del L, we see that the weight of the bar W is acting as an axial load on this bar. But to find the stress at any distance x, that is on this cross section, we see that the load that will be acting on this cross section will be the weight of only this shaded bar. The weight of this shaded bar will be given by W, that x, that is weight on any cross section x, as equal to mg, and the mass will be the mass of this shaded area, which will be rho into volume of this shaded area. The volume of this shaded area is given by the cross sectional area A and the distance x. Therefore, we can write the stress on this cross section as sigma xx is equal to the internal force, which will be equal to load on this cross section xx. The load that will be acting on this cross section will be the weight wx. So we write the stress as wx by the area of cross section, which give us as rho a xg by a. Cancelling area, we get rho g x. Putting it here, we get the elongation as 0 to L rho g x into dx by E. Assuming E to be constant, we get the elongation as rho g L square by 2E. Now, if we see the weight of the entire bar, that is W, we can write it as rho into volume of this entire bar, which will be rho area into length into G. So putting it here, we can get elongation as WL by EA into 2. Instead of rho G, we can put W by AL. L will cancel out, so we will get WL by 2EA. Now, if we look at the formula of elongation del L, we see that the elongation of a bar due to its own weight depends only on the density rho, length L, and material constant E. It does not depend on the area of cross section. That is, if we consider these two bars, one made up of area A and one having area A by 2, but both made up of same material, therefore E will be same. Both made up of same length, therefore L will also be same. We can write the elongation in bar 1 due to self weight as rho g L square by 2E, and in bar 2 as rho g L square by 2E. Since the length of both the bars is same, material is same, so density will also be same and E will also be same. So we will get del L1 is equal to del L2. Therefore, both these bars will elongate by same amount del L. That is, elongation of a bar due to self weight does not depend on the cross-sectional area. Now, elongation in conical bar due to self weight. Conical bar, which is hanged from the ceiling in this manner, the weight of this conical bar will be acting along the axis of this cone, and the weight W will be equal to the rho into volume into G. Now, under this axial load W, this bar will elongate by length del L, which will be given as 0 to L sigma xx by E into dx. Now, if we consider any cross section at a distance x, that is this cross section, we can see that the load that will be acting on this cross section xx will be the weight of only this shaded area. Therefore, the load on this cross section xx will be the wx as equal to the weight of this shaded area, and the weight of this shaded area is given by rho into volume of this shaded area Vx into G. This Vx can be written as the volume of cone, this shaded cone, which will be pi r square by 3 into x. So this r is the radius at any location x and the length of this cone is x. So volume will be pi r square x by 3. Therefore, we get stress sigma xx on the cross section xx as wx by the area of cross section xx. So we get rho g into vx, which is pi r square x by 3, and the area will be pi r square. Pi r square cancel out, so we get rho g x by 3. Putting this value of sigma xx in the elongation formula, we get rho g x dx by 3e. Assuming material to be made up of homogeneous material, so E will be constant, rho will be constant. Taking them out, we get rho g L square by 6e. So again, it can be seen that elongation is not depending on area. So the elongation of this cylindrical bar, which was given by del L is equal to rho g L square by 2e. Now the elongation of cone of same length L as compared to a cylinder of same length L and same material E is 1/3. That is, cone will elongate by an amount equal to 1/3 as compared to that of cylinder. Now consider statically indeterminate systems under axial loadings. Statically indeterminate systems are those in which equation of statics are not sufficient to determine the reactions in the system. For example, consider this system which is fixed from both ends. Suppose an axial load P is applied on this bar like this, and we have to find the reactions which are given at the support A and support B due to the application of load P. To find the reactions, we assume that reaction at end A be RA and reaction at B be RB. It is to be noted that the directions of reaction can be assumed anywhere. It can be either towards the right or towards the left. Similarly, for RB also, it can be towards the left or it can be towards the right. The correct direction will be given after we have written the equilibrium equations. Since this bar is in equilibrium in x direction, therefore net force on this bar in x direction must be 0. Therefore, we can write RA plus P minus RB as equal to 0. Now we have only one equation of statics, that is this equation, but we have two variables RA and RB. Therefore, we cannot find the reactions RA and RB by using the equation of statics alone. That is, using the equations of equilibrium, we cannot find the reactions RA and RB. So this system is an statically indeterminate system. For these systems, additional equation of geometrical compatibility are required to find reactions. For example, in this system, the length of this system is L. This is end A, this is end B. Even after the application of load P, the length of this system must remain L because this bar is fixed from both the ends. Therefore, the equation of geometrical compatibility in this case is that the elongation in bar AB must be equal to 0. That is, length of this bar AB must not change because of the application of axial load P, because this bar is fixed from both the ends. Considering section as C where the load P is applied, we can say that elongation of bar AC plus elongation of bar CB must be equal to 0. Now we have already seen that the elongation in a bar of uniform area due to the application of load P, that is elongation in a bar which is subjected to load P and which is of constant area A and constant E is given by PL by EA. Now consider this bar A, B and here section C where load P will be acting. The reaction at A will be RA and at reaction B will be RB. To find the elongation of this bar AC, we see that the bar AC, that is this bar, is of uniform area A and its length is say some L1. Therefore, the elongation of this bar will be given by this formula. But we have to find the load P which will be acting on the bar AC. To find the load that will be acting on the bar AC, just stand at the end of the bar AC, that is just before the end of the bar AC at this section. Look at all the forces that are acting in the left part of this section. The forces acting in the left part of this section is only RA. Therefore, the load on the bar AC will be RA. Since RA is compressive, therefore we take this load as negative. Therefore, we can write the elongation in bar AC as PL by EA. Instead of P, we put the load as minus RA. Length of this AC is L1, material is E and A. Now, similar is the case with the bar CB. To find the load in the bar CB, stand just before the end of the bar CB. Now look at all the loads in the left of section XX. The loads acting in the left part of the section XX is a compressive load RA, that is this load. Since it is compressive, take minus, and another load is a compressive load P minus P. So this is the load which will be acting at this cross section, that is on bar CB. So to find the elongation PL by EA, instead of P we put minus RA minus P. Let the length of bar CB be L2. Therefore, we get PL2, that is minus RA minus PL2 by EA. This net elongation must be 0. Now, we have another equation containing RA. Using this equation, we can find RA, and we have already seen that RA plus P minus RB was 0. So, putting this RA here, we can find RB. So, we are able to determine reactions of this system only when we have used the equation of geometrical compatibility. Such systems are said to be statically indeterminate system. That is, systems for which reactions are found only when you are using the additional equations of geometrical compatibility. Thermal stresses. When a material is subjected to change in temperature, its length will change by an amount alpha LT, where alpha is the coefficient of linear expansion, L is the length of the body, and T is the change in temperature. It is to be noted that this change in temperature has to be put in degree centigrade or in Kelvin, because change in temperature is same in degree centigrade and in Kelvin. An increase in temperature produces an increase in length. If temperature increases, then length will also increase, and decrease in temperature produces decrease in length. The coefficient of linear expansion alpha is defined as the change in length per unit length per degree change in temperature. So, if the temperature of the body changes by some T degree, then its length will change by alpha into T per unit length. And if the length of the body is L, then its total change in length will be alpha T L. So alpha is per unit degree change in temperature. So when temperature changes by T degree, change will be alpha T, and alpha is per unit length change. So if length is L, then total change will be alpha T L. The units of alpha are therefore change in length, that is some mm, per unit length, which will be some mm, per degree change in temperature, which will be degree centigrade. So cancelling these two, we get the unit of alpha as 1 upon degree centigrade, that is per degree centigrade. Different materials have different values of alpha. So alpha is a material property and materials have different values of alpha. Some have large value of alpha, some have a small value of alpha. Those material that have larger value of alpha will elongate more when their temperature increases. Therefore, the larger the alpha, the larger the change in length. If, however, the free expansion or contraction, free expansion will take place when temperature increases and contraction will take place when temperature decreases. So, if the free expansion and contraction of material due to temperature change is prevented by some external force, then a stress is set up in the material. This stress is called as thermal stress. That is, consider this material which is fixed from both the ends. Let the length of this body be L. Let us assume that the temperature of this body AB increases by some T degree centigrade. Now, due to the increase in temperature, the length of the body will try to increase. But since this bar AB is fixed from both the ends, therefore the length of this bar AB will not be able to increase. Therefore, this bar AB will be under stress as it is trying to expand, but its expansion is prevented by these ends. So, these ends will be forcing this bar to maintain length L, but this bar is trying to expand. Therefore, due to these forces from ends, stresses will be set up in the bar AB. These stresses are called thermal stresses because they have been set up because of change in temperature. To find the magnitude of thermal stress, allow the bar to freely change the length when temperature is changed. That is, if we have this bar AB whose original length is some L and its temperature increases by T degree centigrade, to find the thermal stresses, allow this bar to freely expand. So, we are allowing the bar to freely expand. Here, support was there, the original length was L, this is A, this is B, but we have allowed the bar to freely expand since temperature increases. Therefore, this bar is trying to increase in length by this much amount. This elongation will be alpha TL. As we have seen, when temperature increases by T degree centigrade of a length L, then total elongation will be alpha TL. Now apply a force to return the bar to its original length. That is, apply a force F or P on this bar so that it returns back to point B because it cannot go beyond point B. Now, when an axial load P is applied on this bar, this axial load P will cause a contraction in this bar and the length of this bar will change by amount PL by EA because this bar AB is a bar of length L, uniform area A and material E, and the load is P on this bar. This contraction produced by the load P must be equal to alpha TL, that is this value, so that the bar AB is maintaining the length L. So from here we get P by A as equal to alpha TE. Length will cancel out. This P by A is called as stress, which is alpha TE. So we are able to find this thermal stress. So whenever thermal stress is to be calculated, allow the bar to freely expand or contract and then apply a force to bring the bar to original position. This ends this module.